A horizontal force F is applied to a crate, causing it to move over a rough horizontal surface as shown below. The kinetic friction between the crate and the surface on which it is moving depends on. So we know that kinetic friction is equal to mu k times Fn. So we go through our options. The applied force, no, there's no applied force in this equation. How fast the crate is moving, that's also not there. The surface area, that's also not there. And then the last option, the upward force exerted by the surface on the crate, and that is the normal force. So the answer is D. Question 1.2. Two forces, F1 and F2, can be represented with a single force of 8 newtons. If the magnitude of F1 is 3, which one of the following can be the magnitude of F2? So here we'll just test each one. So 3 and option A is 3. The maximum of those two forces will be 3 plus 3, which is 6, and the minimum will be 3 minus 3, which is 0. 8 does not lie in that range, so A is out. We look at B, so 3 and 4, the maximum is 7, the minimum is 1. C, 8 does not lie in that range, and so that's out. Let's look at C, so 3 and 10, the maximum is 13, the minimum is 7. 8 does lie in this range, and so 10 is an option. So the answer here is C. Question 1.3. Two hypothetical planets can be represented with a single force. Two hypothetical planets, X and Y, have the same mass. The diameter of planet Y is twice that of planet X. So planet X and then planet Y. So if that's R, and if the diameter is double, it means that the radius is also doubled. So that's going to be 2r. If the acceleration due to gravity on the surface of planet X is g, then the acceleration due to gravity on the surface of planet Y will be. Okay, so here I'm going to write g is equal to gm over r squared. And here I'm going to write g is equal to gm, since it's the same mass, divided by 2r all squared. Let's expand this. So that's gm over 4r squared. I'll take out this 4 out front. So 1 over 4 gm over r squared. So in other words, a quarter g. So the answer to that question is A. Okay, question 1.4. A ball is thrown vertically upward in the air. Ignore the effects of air friction. The net force acting on the ball when the ball is at its highest point is. Okay, so we know that any object that's moving through the air is a projectile if the only force acting on it is gravity. So even when it's reached its maximum height, it's still going to have a force of gravity that's pulling it down. It's still going to accelerate with 9.8 meters per second squared. So we can say that F net is equal to ma. And since the acceleration is 9.8, we can say that F net is equal to mg. And mg we know is the weight. So the answer to this question is going to be B. It is equal to the weight of the ball. Okay, question 1.5. Which one of the following statements is always true for inelastic collisions? So remember, for an elastic collision, we have momentum and EK conserved. For an inelastic collision, we have only momentum conserved. So if we're going through our options here, both momentum and kinetic energy are conserved, that's false. Both momentum and kinetic energy are not conserved, that's false. Momentum is conserved, but kinetic energy is not conserved, that is true. So the answer to 1.5 is C. Okay, question 1.6. An object moving horizontally at a constant velocity suddenly encounters a rough horizontal surface. The object continues to move over this rough surface. Which one of the following statements is correct? The net work done on the object during the motion of the over the rough surface is. So when the object is moving over the rough surface, we have W net is equal to F net times delta x times cos theta. Initially, it was moving at a constant velocity, so F net is 0, which means W net is 0. Now it's moving over a rough surface. And if it's moving over a rough surface, it means that there's friction. So the W net is going to be the work done by friction times delta x times cos theta. Now remember, friction always acts in the opposite direction of motion, so it's going to be cos 180. Cos 180 is minus 1, so this whole thing becomes negative, and so the work done, or the net work done, will be negative. So the answer for 1.6 is C. Let's move on. Question 1.7. The hoot of a car emits a sound of constant frequency as the car moves away from a stationary listener. So if that's my listener, and let's just draw a simple car here, it's moving away. Which one of the following properties of the sound heard by the listener will not change? So we know Doppler effect will apply here. Okay, and what is the thing that does not change in Doppler effect? So we go through these options. You have speed, frequency and loudness, wavelength and frequency. Here we don't have to actually do any calculation. Just remember that in the equation for Doppler, so FL is equal to V plus minus VL over V plus minus VS times Fs. The one thing that's constant is V, which is the speed of sound. So the answer here is A. Question 1.8. 2-point charges, each with charge Q, are placed at distance d apart. The force experienced by each point charge has magnitude F. The charges are now doubled and the distance is halved. So we have both charges now with 2Q, and we've now halved the distance. So the force is equal to KQ1 Q2 over R squared. That's original. Now we're going to have F is equal to K2Q1 2Q2 divided by a half R all squared. We halve the distance. Now let's expand the denominator and simplify the numerator. So here we're going to have 4 KQ1 Q2 divided by a half squared is a quarter. Now we can separate this. That is equal to F, and 4 divided by a quarter is 16. So the answer is 16F. The answer is D. Moving on to question 1.9 and 1.10. So 1.9 reads, in the circuit below, the switch is opened. The reading on the voltmeter is. So there's no current flowing through the circuit. And if there's no current flowing through the circuit, the reading on the voltmeter is going to be the EMF of the battery. So the answer is going to be C, 12 volts. Now, you can imagine it as if this voltmeter is connected directly across the terminals of the battery. And so if the voltmeter is connected directly across the terminals of a battery, it's going to read the EMF of the battery, which is 12. Question 1.10. In the circuit below, the battery has an EMF and internal resistance R. With the switch open, readings are registered. Now the switch is closed. How do the readings on the ammeter and voltmeter change? So we go to our formula. EMF is equal to I into capital R plus small r. Let's just open this up. So you're going to get IR plus IR. Remember, this is V external. This is the voltage that we're interested in. And this is V internal. So the first thing we got to do is we got to remember that if you are closing the switch, you are adding a resistor in parallel. Adding a resistor in parallel is going to decrease the total resistance. That means the total current is going to increase. So I total will increase. Now, if I total increases, that's going to have a direct effect on the V internal. So we look at the V internal. So since V internal is equal to I times small r, the V internal will increase. If V internal increases, the V external has to decrease since the EMF is constant. So the answer that we're going to look for is the one that says that the total current increases and the voltage decreases. So that answer is B. A block of mass 15 kilograms is pushed up an incline with a horizontal force F as shown in the diagram below. Okay. The incline makes an angle of 30 degrees with the horizontal. The coefficient of kinetic friction between the block and the surface is 0.2. So that's important, 30 degrees, 15 kilograms. So we'll leave out 2.1, we'll go to 2.2. Draw a labeled free body diagram showing all the forces acting on the block. So the block is on an incline, so it's going to experience a force of gravity straight down. And because it's on the incline, it's going to experience a normal force, and it's in contact with a surface, and the normal is going to go like this, so Fn. It's also experiencing a force applied that's horizontal to the left. It's a bit unusual, but that's what it is. And it's going up a rough surface. There is kinetic friction, and since it's going up, the friction is going to act down the slope like so. So 4 marks, 4 forces. Question 2.3, the block moves up the plane at a constant velocity. So constant velocity is quite important because it tells us that the acceleration is 0, and it also tells me that the F net is 0. 2.3.1, state Newton's first law. Okay, we're leaving that out. 2.3.2, calculate the magnitude of the force F. Now, what I want to do first is I want to draw the forces with their components, because the components are going to make it a bit more easier for me to figure out what's equal to what. So 2.3.2. So I'm going to have the gravity, the force of gravity, and it's going to be broken up into components. You'll have one component of gravity this way. Now this is not part of my answer, so I can draw it. This is going to be Fg perpendicular, and that is going to be the normal force, so Fn. Then the gravity is also going to have a component going this way, which is Fg parallel. It's also going to have a frictional force. And now we need to think about this force applied. Is that force applied going to have any components? So we go here and let's draw it out. So here's my force applied. So force applied here. Now there is going to be a force that goes up the incline. Let's call it F up. And it's going to be 30 degrees since the angle given here is 30 degrees. And then that means there's also going to be a force this way. Now, let's assume we don't know this angle and we don't know what this force is going to be. But these two forces, this one here and this one here, will give a resultant of Fa. So the Fa is going to have two components. Now, it's not important what we name it for now, and nor is it important the angle. Let's just include it. So there's going to be a force here. Now let's call it force down, just for simplicity. And then there's going to be here F up. So we have our forces, right? And now since the object is moving up this way, I'm going to choose that direction as positive. And what I can get from here is that since F net is equal to 0, I can say that this force here is going to equal the sum of these two forces. And from there, I can then work out what F is. So let's go with that. So we'll say that F net is equal to 0, since it is at constant velocity, like we said. Now, So F up, and so F up minus friction minus FG parallel is going to equal to 0. Now we need to start looking at components. So let's take these three forces and make a triangle out of it. So I can take the force up like so. I can take the force down like so. And then the force itself is going to be here. Now you notice that this is 90 degrees. And this right here is 30 degrees, which would mean that this is going to be 60 degrees. Now we can use trigonometry to work out what F up is going to be and what F down is going to be. So if you want to work out what F up is, let's use this 30 degrees. So we can say that, so this is going to be the hypotenuse, and this is going to be adjacent. So I can say that cos of 30 degrees is equal to F up divided by F. So that means F upward is going to equal F times cos 30. So this is obviously important. Then let's look at F down. So F down is going to be, we can use sine for that. So we'll say sine of 30 degrees is equal to F down divided by F. So that means F down is equal to F times sine 30 degrees. So we're interested in those two. We also need to know what friction is going to be. So let's take a look at friction. So friction we know is equal to mu k times Fn. Now if we look at our forces here, Fn is actually going to equal F down plus Fg perpendicular. So Fn is equal to F down plus Fg perpendicular. Now we said that F down is going to be F sine 30, and perpendicular here. Perpendicular is going to be mg cos theta. Well, we know theta is 30 degrees, right? So that means we can take this and calculate F. So F is going to equal, well, mu k they gave us as 0.2. So 0.2 into F sine 30 plus, the mass was 15, so 15 times 9,8 times cos of 30. And this is going to be the friction value. So we have the friction, we have F up, and the only thing we don't have, we can work out is Fg parallel. So we'll take all of that, we'll substitute it, and then we can solve for F. So F up we said is F cos theta. So F times cos 30 minus the friction we said was 0.2. So 0.2 into, that's 15 times 9,8 times cos 30 and plus F sine 30. And we'll continue in the line below, and we're going to minus from this. Fg parallel is mg sine theta. So 15 times 9,8 times sine 30 degrees. And that's equal to 0. If you notice now, the only thing we don't know is F. And we can solve for F. So F is equal to 129,19 newtons. Okay, let's take a look at the last question, 2.4. So a satellite that is 1,000 kilometers above the surface of the Earth is accelerating toward the Earth. The weight of the satellite at 1,000 kilometers above the surface of the Earth is 3,800 newtons. Calculate its weight on the surface of the Earth. So here 1,000 kilometers. Here's my satellite, 1,000 kilometers. Then there's my satellite. Its weight is equal to 3,800 newtons. And remember, we still have to account for the radius of the Earth. Okay, and they want to know what is the weight on the surface of the Earth. So what I'm going to do here is I'm going to actually calculate what is the acceleration due to gravity at this point here. Right, and we can calculate that by using G is equal to Gm over R squared. So G is 6,67 times 10 to the negative 11. The mass of Earth is 5,98 times 10 to the power 24 divided by, so what is the radius? The radius of the Earth is 6,38 times 10 to the power 6 plus the 1,000 kilometers. So plus 1 times 10 to the power 6 and then all squared. And this is going to give us a value of 7,32 meters per second squared. Now from this, we can work out the mass of the object since we have the weight. So we'll say that Fg is equal to mass times gravity. Fg is the weight, so 3,800 is equal to m times 7,32. We can then get the mass of the object as 518,88 kilograms. Now that we have the actual mass, the mass of the substance doesn't change, so we can calculate its weight on the surface of the Earth. We can say Fg is equal to 518,88 multiplied by 9,8 since it's on the surface of the Earth, and that's going to give us a weight of 5085,05 newtons. A ball of mass 0.5 kilograms is dropped from a height of 1.2 meters on a hard floor. So 0.5 kilogram block dropped 1.2 meters on a hard floor. Okay, it bounces to a maximum height of 0.8 meters. So it bounces upward, there's a 0.5 and goes 0.8 meters. The floor exerts a force of 15 newtons on the ball. So this is going to be 15 newtons upward since the floor is exerting the force on the ball. Now 3.1, write down the magnitude and direction of the force that the ball exerts on the floor. So Newton's third law would say that it's going to be equal in magnitude but just in the opposite direction. 3.2.1, calculate the velocity at which the ball strikes the floor. So I'm going to write down the quantities that we know. They tell us it's dropped, which means that VI is 0. Delta Y, I'm going to choose down as positive, and so delta Y is going to be 1,2. That means acceleration is also going to be 9,8 positive value downward. Now I can calculate VF. So VF squared is equal to VI squared plus 2A delta Y. We'll substitute in here. So 0 squared plus 2 into 9,8 times 1,2. Now don't forget to square root at the end. So VF is going to equal 4,85 meters per second downward. Now moving on, 3.2.2. Calculate the time taken by the ball to reach the floor from the moment it dropped. Now that we know VF, we can use the simple equation VF is equal to VI plus A delta T to help us calculate the time. So VF we worked out as 4,85, and that's equal to 0 plus 9,8 times delta T. Now delta T then is going to equal 0,49 seconds. All right, now question 3.2.3 says, calculate the speed at which the ball bounces off the floor. So the speed, if you think about the information that we know, so it reaches a maximum height at 0.8. So that means here it's stopping. So VF is 0. We don't know VI. We know that the acceleration is 9,8. And since we chose down as positive, the ball is moving up in this direction. So it means that the 0.8 needs to be minus 0.8, and acceleration will remain as plus 9.8. So 3.2.3, if you write down the information that we know, Vf is 0, acceleration is going to be 9.8 downward, and since we chose down as positive, the displacement, the delta y, is going to be minus 0.8. Now we can use this information to calculate Vi. We can use Vf squared is equal to Vi squared plus 2a delta y. So Vf is 0, Vi is what we want, plus 2 times 9.8 times minus 0.8. Now, when we solve for Vi, again, don't forget to square root, we're going to get an answer of 3.96 meters per second. Remember, they wanted speed. Speed is a scalar, so we do not need to give direction, though the direction is going to be upward. Question 3.2.4, calculate the time that the ball is in contact with the floor. So we want the contact time. So to get contact time, we can use the equation F net delta T is equal to delta P, where delta T is our contact time. Now we don't know what F net is. So let's draw a free body diagram just quickly on the side here. When the ball hits the ground, there's two forces acting on it. There's the force of gravity and there's the force upward. That's the force of the ground on the ball. They told us that that is 15 newtons. Now, if we choose up as positive this time, F net is going to be the 50 minus Fg. And we can calculate Fg by saying mass times gravity. So if we subtract them, we're going to get a value of 45.1 as my F net. So F net is going to be 45.1 times delta T, and that's equal to delta P. Well, delta P is the mass, and then the final velocity, well, we know that it rebounds off the ground with 3.96, and we chose up as positive, so it's positive 3.96, and then minus the velocity that it hit the ground with. So I can just sketch it for you here. It hits the ground with 4.85. So 4.85, and it goes up at 3.96. Now if I chose up as positive, that's going to be positive, but that's going to be negative. So it's going to be minus 4.85. So we're actually adding that 4.85. And so when we solve for delta T, we're going to get an answer of 0.097 seconds. And now question 3.3, the last question here. Sketch a graph of position versus time. So here and here, position, and then time here. And then we want to know the height from which it is dropped. So it's dropped from 1.2. It takes 0.49 seconds. So 0.49 here. So it's going to go down, hit the ground there. Then it's going to be in contact with the ground for 0.097 seconds. So we add that on. So this is going to be 0.59. And it rebounds upward up to a maximum height of 0.8. And that is our position time graph. A bullet of mass 6 grams is shot horizontally into a 194 gram wooden block, which is at rest on a horizontal surface. The bullet hits the block with a velocity of 200 meters per second and remains stuck in the block. Ignore the effects of friction. We leave out 4.1. 4.2 says calculate the speed of the block bullet system immediately after the bullet struck the block. So this is a momentum question, and we'll look at the conservation of linear momentum. So 4.2 says we will do that. The total momentum before is going to equal the total momentum after. So we're going to say the mass of the bullet times the velocity of the bullet plus the mass of the block times the velocity of the block is going to equal, and Afterward, we're going to add them because they're moving as one system. So the mass of the bullet plus the mass of the block times the velocity. Now it's just a matter of substituting. So the bullet has a mass of 6 grams, so that's 6 over 1,000 because it needs to be in kilograms. The velocity is 200, and we'll choose right as positive. Plus the block is 194, and it has a velocity of 0, it's stationary. Afterward, we're going to add, so 6 plus 194 is 200, so 200 grams divided by 1,000 times V. And now we're just solving for V. So V is then equal to 6 meters per second. Since it's positive, it means that it's going to be moving to the right. Okay, immediately after the impact, the bullet block system enters a rough section PQ, which is 5 meters long, before coming to rest. So it's important, it comes to rest. Calculate the acceleration of the bullet block system. So we know that it comes to rest, so Vf is going to equal 0. This 6 actually then is the Vi, and it's traveling 5 meters, so delta x is 5. So we can use the equation Vf squared equals Vi squared plus 2a delta x to solve. So Vf is 0, Vi is 6, so 6 squared plus 2 times a, and then delta x is 5. Now to solve for a, just use a calculator. So a will be minus 3.6 meters per second. Now, since we chose right as positive earlier on, this is actually to the right. We can't leave our answer as negative, so we will change it. So a is equal to positive 3.6 meters per second squared, and that's going to be to the left. Okay, moving on. 4.4. A box of mass 60 kilograms slides down a rough inclined plane which makes an angle of 25 degrees with the horizontal. The box experiences a constant friction of 180. Draw a label free body diagram showing all the forces acting on the box. So 4.4.1, as it's going down the incline, it's going to experience force of gravity. It's going to experience friction upward, parallel to the surface since it's going down. And there's going to be a normal force that is perpendicular to the plane. So 3 marks, 3 forces. Yeah, that's it. So 4.4.2, write down the name of the force which does 0 work on the box. So remember, to calculate work is equal to F times delta X cos theta. Now if cos is 90, well, if theta is 90, that's going to make, remember, cos of 90 is 0. That's going to make the entire thing 0. So we ask ourselves, which is the force that is acting perpendicular to the direction of motion? And that's the normal force. So the normal force is the one that's doing no work or 0 work. Let's move on. The box now passes point A on the incline at a speed of 4 meters per second before passing point B, which is 15 meters lower down the incline. Calculate the kinetic energy of the box as it passes point A. So point A, okay. So we're going to say 4.4.3 EK is equal to half mv squared. So half, the mass is 60. They've given us the velocity at A. The velocity at A is 4, so 4 squared. And that gives us an answer of 480 joules. Okay, 4.4.4, calculate the magnitude of the resultant force acting on the box between point A and point B. So 4.4.4, if we go to our free body diagram right here, and we consider what is F net going to be. So this gravity actually has 2 components. It's going to have a component going here, that's FG parallel, and it's going to have a component going here, which is FG perpendicular. The perpendicular is going to equal the normal, and so the only 2 forces are going to be the FG parallel and friction. So F net, assuming down is positive, is going to equal FG parallel minus friction. So to calculate this, we just need to say that F net is equal to FG parallel minus friction. Now FG parallel is mg sine theta minus friction, which they've given us as 180. Now we just need to substitute. The mass is 60, gravity is 9,8, and then sine of the angle of elevation, that is 25 degrees, and then minus 180. So that gives us an F net, or a resultant, of 68.5 newtons. 4.4.5 we'll leave out. 4.4.6, use the work energy theorem to calculate the speed of the box as it passes point B. So 4.4.6, we will say that the net work done on an object is equal to its change in kinetic energy. So W net can be rewritten as F net times delta x times cos theta, and that's going to equal, so EK final, so it's going to be actually the EK at B minus the EK at A. F net we know is 68.5, so 68.5, the box travels 15 meters, and it's going to be cos of 0, since we chose down as positive, and F net is down anyway. That's going to equal the EK at B, and then minus the EK at A. We worked out the EK at A as 480. Now we can solve. We can say that 68.5 times 15 times cos of 0, which is 1, plus 480 is going to equal half times 60 times the velocity at B squared. Now we solve for VB, and don't forget to square root. VB is going to equal 7,09 meters per second. A 200-watt motor operating at 85% efficiency pulls a crate of mass 90 kilograms up a slope at a constant speed of 1.5 meters per second. It takes 30 seconds to raise the crate from point X to Y of the slope. We'll skip 5.1. 5.2 says calculate the energy supplied by the motor to the crate in 30 seconds. So 5.2.1, well, we know that the power is going to be 85% of 200. So 85% of 200 is 0.85 times 200 is 170. So the motor is actually working at 170 watts. Now, we know that work is equal to power times time. So 170 times 30, that gives us 5,100 joules. 5.2.2, calculate the gain in potential energy, or gravitational potential energy rather, of the crate between X and Y. So basically we're working out EP, which is mgh. The mass is 90 kilograms, gravity is 9,8, and it went up 3 meters. That gives us a gain of 2,646 joules. Now 5.2.3, calculate the magnitude of the frictional force acting on the crate between X and Y. So the first thing I'd like to do is I want to work out what the actual distance is. What is the distance between X and Y? So we can use V is equal to distance over time because it's constant velocity. So 1.5 is equal to distance divided by 30. So 45 is equal to distance. So this distance right here is 45 meters. Now, if I draw a free body diagram showing the forces that's acting on this object, we'll have a normal force here. We will have a force of the motor. We'll have a frictional force. We will also have the parallel component of gravity, and we will have the perpendicular component of gravity. Now, F net is going to equal 0 since it's moving at a constant velocity. Now, if I've chosen up the slope as positive, the force of the motor minus friction minus Fg parallel is going to equal 0. Now, I can relate this to the work energy power, rather the work energy theorem. So W net is equal to 0, and that's because F net
is equal to 0. That means the work done by the motor minus the work done by gravity minus the work done by friction is going to equal 0. So we know the work done by the motor, we've worked it out. So 5,100 minus the work done by gravity is 2,646 minus the work done by friction is equal to 0. So we can simplify. So 2,454 minus, now let's expand this. The work done by friction is going to be friction times delta x. We don't need to include the cos theta here because the minus is already taking care of that. And that's equal to 0. Now we know delta x, we've worked it out as 45. So 2,454 minus 45 times f is equal to 0. Now we just solve for f. F is equal to 54,53 newtons. A traffic officer is sitting in a police car which is traveling at a constant velocity. The siren of the police car emits sound waves of frequency 1500 Hertz. So I'm just going to quickly sketch out a police car here. It does a police car. Frequency of the source is 1500 Hertz. A detector placed on the side of the road records a frequency of 1695 Hertz. So if that's the road, there's a detector here, that's the listener, and the frequency is 1695 Hertz. The police car takes 1.5 seconds to reach the detector, so time is equal to 1.5 seconds. So we'll skip 6.1 and 6.2. We'll go straight to 6.3, which says calculate the distance between the police car and the detector. First, we should work out the speed of the police car. So we'll go to our equation. FL is equal to V plus minus VL over V plus minus VS times Fs. Now, since they are approaching one another, we will have a big top and a small bottom. So the equation will be FL is equal to V plus VL over V minus Vs times Fs. Now let's substitute. The listener is 1695. The speed of sound in air is given as 340. The listener is not moving, so it's plus 0. Divided by 340 minus Vs, which is what we want, times the frequency of the source, 1500. Now we just solve for Vs, and we will get 39,12 meters per second. Now, since we know that it's moving at a constant velocity, we can use V is equal to distance over time to solve for distance. So the speed is 39,12. That's equal to distance divided by 1.5. That means distance is going to equal 39.12 multiplied by 1.5, which is 58,67 meters. Okay, 6.4, draw a graph of the frequency heard by the traffic officer sitting in the police car. Now this is, you could think of it as a trick question because the traffic officer is sitting inside the vehicle. So the frequency that the traffic officer is going to hear is going to be the frequency of the source. It's not going to be changing at all. And so if you have to draw the graph, it's simply going to be 1500 here, straight across, and 1.5 seconds when he reaches the detector and when he passes the detector. So there's no change in the frequency heard by the traffic officer because he's sitting inside the vehicle. 3 point charges X, Y, and Z with charges -3 microcoulombs, 6 microcoulombs, and 9 microcoulombs respectively are placed on insulated stands as shown below. We leave at 7.1. 7.2 says calculate the net force acting on point charge Z. Okay, so to answer this question, we will need to work out, so what is the force of X on Z, and then what is the force of Y on Z? We can calculate this using K Q1 Q2 over R squared. So X on Z, that's going to be 9 times 10 to the 9. X is 3 times 10 to the minus 6. Remember, when you're using this formula, you do not need to include the negative sign. And Z is 9 times 10 to the negative 6. That's divided by R squared. How far apart are X and Z? They are 15 centimeters, which is 0.15 meters squared. And that is equal to 10,8 newtons. Now, we need to put a direction here. So if you look at it, X is negative, Z is positive. So Z is going to be attracted to it, so it's going to want to go to the left. So we'll put an arrow just to show us left. So that's done. Now we need to do F of Y on Z. So F of Y on Z, that's going to be 9 times 10 to the 9. And then Z is 9 times 10 to the negative 6. Y is 6 times 10 to the negative 6. And that's divided by 0.1 all squared. That gives us an answer of 48.6 newtons. And what direction is this going to be? So since Y is positive and Z is positive, Z is going to want to go to the right. So that's going to be to the right. Now F net is going to be the sum of these two, but they are in opposite directions. So we should subtract them. I'm going to choose right as positive here. So it's going to be 48.6 minus 10,8. And that's giving me an answer of 37.8 newtons to the right. Okay, 7.3. Point charges X and Y are brought into contact and then separated. Point charge X is returned to its original position, while point charge Y is removed. In which direction did electrons flow? So electrons will flow from the more negative to the less negative. So if you're looking at X and Y, X is clearly more negative since it has a negative charge. So it's going to go from X to Y. 7.3.2, calculate the number of electrons transferred. So to calculate the number of electrons transferred, that's going to be the final charge minus the initial charge divided by the charge of an electron. We need to work out QF. So to work out QF, we'll do Q is equal to Q1 plus Q2 over 2. So minus 3 plus 6 divided by 2, that's 1.5 times 10 to the minus 6 coulombs. So this is my QF. Now we can substitute. QF is 1.5 times 10 to the minus 6 minus, I'm going to use X as my reference. So X was minus 3 times 10 to the minus 6. And then that's divided by QE, which is minus 1.6 times 10 to the minus 19. Since we want n as a positive number, we'll just take the positive value. So n is going to be 2,8125 times 10 to the 13 electrons lost by X. Now 7.3.3, point T is placed between point charges X and Z. Okay, so let's quickly just draw a diagram to show what's going on. So I have X here, I have Z here, and now T is somewhere here. Now we know the distance between these two was 0.15. So they want to know, calculate the distance between point charges X and T where the net electric field is equal to 0. Okay, so if the E net is equal to 0, it means that the F net is equal to 0. So in other words, the force of X on T would be the same as the force of T on Z, or the electric field at X on T, at at t due to x will be equal to the electric field at t due to z. So all we need to do is equate the electric fields. So we'll equate the electric fields. Remember, electric field is kq over r squared. And that's going to equal kq over r squared. Now, 9 times 10 to the power 9. X has a charge of 1.5 times 10 to the minus 6. Remember, that's the new charge that it currently has, divided by. Now, the question is asking the distance between x and t. So let's call this x. Therefore, this is going to be 0.15 minus x. So between x and t is going to be x. And that's equal to, well, x squared rather. And then this is going to be 9 times 10 to the 9. Z has a charge of 9 times 10 to the minus 6 coulombs divided by, what is the distance? 0.15 minus x all squared. And now we just solve. So x is equal to 0.04 meters. Question 8 reads, the battery in the circuit below has an EMF of 12 volts and an internal resistance of 0.3 ohms. The resistance of the connecting wires and ammeter can be ignored. We'll leave out 8.1. 8.2 says determine the total external resistance of the circuit. So this 8 and 5 ohm resistors are in series. So 8 plus 5 is 13 and 4 plus 3 is 7. So if I want to work out the total resistance here, I can just do product over sum. So 8.2.1, the resistance is going to be 13 times 7 divided by 13 plus 7, and that is 4.55 ohms. 8.2.2, let's clear this up. Calculate the reading on ammeter A. So ammeter A is reading the total current of the circuit. So EMF is equal to I into big R plus small r. We'll substitute. 12 is equal to I into 4.55 plus internal resistance 0.3. The total current is then going to equal 2.47 amps. Question 8.2.3 reads, calculate the current through the 8 ohm resistor. So to calculate the current, remember I is equal to V over R. I need to know the voltage that the 8 ohm resistor is going to, well, that branch is going to be using. So it's not going to be 12 because the V external is going to be less than 12 because some is going to be lost due to lost volts. So I can work out the V external. V external is equal to I times R. Total current is 2.47. Total resistance was 4.55. And that's equal to 11.26 volts. That means only 11.26 volts out of the 12 volts is available for the circuit. And since the two branches are in parallel, it means that each branch is going to be using 11.26 volts. So I can work out the current. So it's going to be 11.26 divided by the entire branch is 13 ohms. Remember, the current going to the 8 ohm is going to be the same current going to the 5 ohm. So we have to take the entire branch. So it's going to be divided by 13, which is equal to 0.86 amperes. Now let's move on. The next part of the question says the voltmeter V2 with a very high resistance is now placed between points X and Y as shown in the diagram below. Calculate the reading on voltmeter V2. So remember the V external is equal to 11.26. Now we can work out what each resistor is going to be using. So let's consider the first branch, which is the 8 ohm resistor and the 5 ohm resistor. So we want to divide this 11.26 in that ratio. So 8 to 5, that's total 13 parts. So we'll do 8 divided by 13 times 11.26. That means the 8 ohm resistor is going to be using 6.9 let's get this with a pen, 6.93 volts. It then means that the 5 ohm resistor will be 5 over 13 times 11.26, which will be 4.33 volts. Now we repeat the process here. We're going to have the 4 ohm and the 3 ohm. Total parts 7. So 4 over 7 times 11.26, that is 6.43. So this will be 6.43. And then 3 over 7 times 11.26, which will be 4.83. And this will be 4.83. Now to work out V2, it doesn't matter which 2 you subtract. Just for the sake of simplicity, let's subtract this and this. Well, this voltage and this voltage. So V2 is going to equal 6.93 minus 6.43, which is 0.5 volts. Now, even if you subtracted the other 2, this one and this one, you'll still get 0.5 volts. 8.4 says when the 8 ohm and 5 ohm resistor alongside are removed, the reading on the voltmeter increases. Explain this observation. So if you remove resistors in parallel, the total resistance will increase. That means the total current will decrease. Now we got the equation EMF is equal to V external plus V internal. And remember, V internal is I times small r. So if I total decreases, V internal will decrease. That means V external will increase since EMF is constant. Now moving on to the last question. The cost of energy is 259 per kilowatt hour. How many 80 watt bulbs can you have on for 8 hours per day if your budget for lighting is 300 a month? Assume that an average month has 30 days. So remember, cost is equal to the amount of energy that's used multiplied by the tariff. So the tariff is how much the municipality or whoever is charging you for the usage of that electricity. So first thing we need to do is we need to convert. So 8 watts is equal to 0.08 kilowatts. Now for an 8-hour day, it's going to be 0.08 times 8, which is 0.64 kilowatt hours. Now for 1 month, we multiply this by 30. So 0.64 times 30, which is now 19.2 kilowatt hours. This is for a month, and this is for 1 bulb. So we can work out the cost for that 1 bulb. So 19.2 times 259. So that 1 bulb is going to cost 49 Rand 73 cents for 1 bulb. So if you had 300 Rand and you wanted to work out how many bulbs you could use, you'll just need to say 300 divided by 49,73, and that is 6 bulbs. You can have 6 bulbs on for 8 hours a day for 30 days if the bulbs are 8 watts.